All right. Good afternoon, everyone. Welcome to our panel on advances in air quality modeling, current and future. Uh, so as many of you know, models such as CMAC are in state of constant scientific evolution. And in the spirit of that evolution, uh, the theme of this session is sort of representing the current state of the models, as well as uh, where we are likely to be headed in the future. So we have, the way we've tried to structure this panel is we have two talks, uh, and the first talk will be given by Sergey Napelenok, and he will talk to you briefly about some recent updates in the CMAC modeling system. So as many of you are probably aware, there was a new version of CMAC version 5.3.2 that became available publicly a couple of weeks back. So Sergey will talk about some of the updates in that system, predominantly focusing on the source apportionment method, advances in that method that have been implemented, sort of representing the current state of the model. And then the second talk is by Dr. John Pleim, and John will talk about some of our thinking related to uh, what we are calling the advanced air quality modeling system. And this is sort of looking ahead in terms of where we anticipate the application needs of the models and how the models need to evolve to address those needs. The way we're going to try and structure this panel, so we have two talks. After each talk, we'll try and keep some time for question and answers. Please use the chat box, the Q&A chat box, which you see on your screen to submit your questions. You can do that as the talks are going through, and then once each speaker has completed their talk, then we can get into the Q&A session. So with that, let me hand it over to Sergey.
Hello, this is Sergey Napelenok from USCPA. I'm going to start sharing my presentation. Just welcome everyone to the afternoon session. Just to let everyone know, I am having a little bit of connectivity and audio issues. So if I cut out, Rohit will let me know and we'll back up a little bit. Is it working?
Yes, we can see us.
Okay, as soon as this starts, there we go. So this, what I'm talking about today is really the source apportionment updates that we did in CMAC 5.3.2, 5.3.2. This, as you can see, was a work of many people on the ISAM CMAC team that I have listed here. Let me just go ahead and jump right into it. So everyone in this audience probably knows why we work on developing air quality models. And we all also know that these models are probably not 100% always correct. But what we try to do is to make them useful for people. And one way that these models, did I skip one? These models are used is to for regulatory applications where people are really interested not in just the emissions or signal that translates to concentrations in deposition, but really the relationship between the emissions and the concentrations. One way to do that is what's really easily understood as the brute force method, where you just run the model once with your regular emissions, meteorology, and all the inputs, and then you repeat that simulation again with some parameter that has been changed. And then you take the difference, and that's your brute force method response. Well, actually, we probably want to be a little bit more fancy in how we do this and make it a little bit more easier for people. So over the years, various tools have been developed to provide that kind of signal between emissions and concentrations, or meteorological inputs and concentrations, or any other model parameters. And so these tools, I have some of them listed here for CMAC, we've had things like a CMAC decoupled direct method in 3 dimensions, CMAC adjoint, various types of response surface models. And then the one that I'm talking about here today is the CMAC ISAM, which is integrated source apportionment method. Now, this CMAC ISAM is an apportionment technique that is embedded within the base CMAC model and released directly with the CMAC model, starting from the last release that we did. And really, the goal of CMAC ISAM is to quantify the various emissions contributions from either source sectors, like, for example, EGUs or mobile sources or fires, and also geographic regions, like various states or countries or smaller regions. And then we want to quantify these impacts on both the concentrations of the pollutants and also their deposition amounts. So just a brief history of this method in CMAC so far. Essentially, from the very beginning of CMAC, people in various groups have been asking for source apportionment capability to be included in the model. And in fact, people from outside of our group at EPA have contributed and developed their own ways to calculate apportionment within CMAC. Unfortunately, these outside contributions have not always stuck around because people developing them have moved on to various other projects, or if they were students, they graduated and got jobs in different fields. And we never really picked up, or were able to pick up and share and continue on with this, whatever their contribution may have been. But in about the year 2010, we established a collaboration between 2 different offices in EPA. That is the Office of Air Quality Planning and Standards, that's the regulatory kind of office, and the office where I am in, which is the R&D office of EPA. And we wanted to explore implementing source apportionment in CMAC that would be supported by our group and released in subsequent releases of CMAC. And then 2 years later, we did release the first version of ISAM for only PM species, and that was in version 4.7.1. And essentially, the way that we did that is we waited till the base model was released, the code was frozen, then we went through the code and implemented this release, and then released that to the public. A year later, we extended the method to ozone calculations. This is secondary production of all the various ozone precursors, the NOx species, all the different VOCs in the model. And then we also, at the same time, you were able to look at apportionment of these precursors and all of the species explicitly. Now, since then, so starting in about last year in the CMAC version 5.3, we decided to integrate ISAM with a base model release. And at the same time, we wanted to address some of the user concerns with this method. One was, the biggest one really, that the method was really too slow. And if you wanted to track a substantial number of sources over the domain, that you would at some point get to a situation where it wasn't really feasible with any reasonable amount of computational resources. And regional scaling, because that is exactly what you're doing with ISAM, is tracking emissions and regions. So we released this version in 5.3, and unfortunately, very soon after the release, other people's applications and our own and outside groups identified some issues with the gas phase algorithms. So we wanted to address those issues as soon as we could. So earlier this year, about mid-April, we assembled the ISAM work group, which is all the people I listed on the co-authors of this presentation. ISAM predictions for ozone and other secondary gas phase species. And I'll show you in a minute what the problem was. And in the future, we'll continue developing and refining this method and extend it to other species, for example, SOA, but are not currently included. And as always, we look forward to feedback from the users that apply this on various episodes, various configurations, various computer environments, because that is really the best way to test how okay, I'm gonna wait a minute. I may have been stuck. Looks like I'm back, so I'm gonna continue assuming that I am back. So the issue with the previous release, which was again version 5.3.1, is essentially the way that ISAM works is the user specifies various tags to, yeah, looks like I am back. Sorry, I apologize for that. The user specifies various tags that they want to track, various sectors or geographical regions and whatnot. But the user typically doesn't specify all of the tags, which is either unwanted or impossible, in which case all of the other streams and other emissions and other sources get tagged into this tag that we call other, which, so this is stuff that you're tracking and then stuff that you're not tracking. And unfortunately, the issue was with the previous release that the method was erroneously over attributing to this other category. Essentially, a lot of the mass was going to this other category where it didn't belong, and it was really a problem with the way the implementation of the method was done. So, and like I said, we've noticed this pretty soon after the release when other people started applying it to their cases. So what's new in this model release? As I said, the main focus of this release had been on CMAC ISAM, but there are also other things that changed in CMAC. And I would encourage any user of CMAC to go ahead and upgrade to this method or to this version, because very many important bugs and kind of quality of life improvements were also added in this 5.3.2 that were done outside of ISAM. So essentially, if you're a user of CMAC, and even if you don't care about ISAM, I really encourage you to go ahead and get this new version. And you can get more specific about what else was done to it in the documentation that was provided with the release. And also, there's probably other presentations in this conference you can go look at to see what else we did. Now, how did we change ISAM? Kind of for a quick summary. Instead of what we're doing before, we now want to track the production and loss terms for each chemical reaction. Essentially, we look at all of the reactants and all of the reactions, and consequently, this is available for every mechanism released in CMAC because it's done automatically. And it's taken advantage of similar methodology that was done for IRR, which is the integrated reaction rate. And then we propagate the changes from each reactant participated in every reaction in CMAC based on the stoichiometry and the production loss rate equations of the precursors. So now I can't really explain exactly 100% of all the math that went behind the model, but I can give you a little bit of a preview in the next few slides. So essentially, this is an analytical solution. So, and the first thing we do is calculate the bulk production rate for each reaction. That's this term PT of each for all species. And essentially, it's a function of all the stoichiometry and all the reaction rates that CMAC already calculates anyways. Now we also can calculate the initial tagged fractions of each species. And those initial tagged fractions at the very beginning of the simulations, it's essentially what the emissions are releasing and the concentration array is being populated. And since we are tracking the emission streams in ISAM, we can already separate them into the appropriate tags. So this P quantity is just a fraction of the tagged reactant concentrations over their bulk quantities. And then we can also calculate for every source, we can calculate the probability that none of the reactants came from the source, because the probability of something happening is essentially 1 minus the probability of that thing not happening. And that is useful in this next equation because we can use it to calculate the fractional contribution from each reaction. And I'm not going to show you how to solve this quantity because it's a bit more involved than I have time for, and it depends on what kind of a reaction you have. For example, if it's just one species that decays into various products, or if it's a bimolecular reaction, or if it's a reaction on a surface of something. All of those things require different solutions. But the point is, we can now use the solution to split the production by the source according to this formula below. Now, when we have that split from each bulk reaction by the source, we can now use that to apportion it to our products of the reactors, essentially. And here we turn a little bit more into an engineering approach versus the purely mathematical approach that I outlined earlier. That we make kind of an assumption. Now, if the bulk production is a positive thing, that's different. That means mass is being produced from that reaction. If it's not positive, that means mass is being destroyed. And the apportionment of that destruction is fairly straightforward, and we assume that it's proportional to the amount of the reactants that were there at the beginning. Now, if it is positive, and we do have production simultaneously with destruction, then we need to solve the production loss ordinary differential equation to distribute the mass for the time step. Now, if you are interested in more math on how this is done, there are documents being released with this model, and there's an update to the ISAM chapter in the user's guide. And additionally, there is an entire chemistry, I think it's called an appendix or addendum at the end of that document that you could see just the math behind chemistry and ISAM in the new release. Now, there are a couple of weaknesses to this method, and I didn't really talk about them yet, but I want to kind of point them out. There's two main weaknesses so far that we've noticed. One is because these methods aim to calculate this apportionment efficiently or quickly on the computer, we don't explicitly track all of the species. And in fact, one of the problems that was leading to that over-attribution to the other category in the previous release was the fact that we did not track enough species. And in this release, we did add more of the radicals and intermediate species in the ozone production mechanism. But still, we're not tracking everything. And this introduces some error from the species that are not tracked. And if you are interested if your application does require kind of seeing the picture, the complete picture of the chemistry in your application, then other tools exist that I would point you toward those instead of ISAM. And these are things like sensitivity analysis in the forward sense, in the reverse sense, or even the IRR. Now, the other weakness is kind of more subtle, and that comes from the fact that ISAM always tracks more than one thing. Even if the user just specifies one thing, the model automatically also tracks contributions from boundary conditions, initial conditions, and this, like I said, other source. And these sources also chemically and physically interact with one another, and there essentially leads to this mathematical cross product of their fractions that are applied to each source, which means that this method and the results are sensitive to the number of sources, because if you have more sources, you have more cross products, and the cross products are different between each sources because you have more of them. So generally, the method approaches kind of a theoretical minimum for error from this phenomenon when you track more and more sources, which is kind of backwards from what I'm going to tell you later, which is where you want to track less sources to make it go faster. But theoretically, mathematically, your answers are better when you track more things. Now, also from the same phenomena, if you track a smaller number of sources, the contribution from any given source will be higher than with a larger number of sources. And that is a little bit counterintuitive, but if you just run this thing a couple of times, you will notice what I'm talking about immediately. And again, there is more documentation released with this code that you can go read further. Now I told you a little bit of what we did. I'm going to just show you a brief demonstration of what it's capable of. First thing I'm going to show you is on a hemispheric scale. It's not really important what we're modeling here, but here it is. Essentially, here is an example of what was the typical output of ISAM in the previous release. So here, this is a hemispheric scale application. We're tracking various sources, and the first panel here is the bulk ozone concentration, And then we have contributions from things like the potential vorticity injection on the upper levels. We have anthropogenic sources, we have biogenic and fire sources, boundary conditions, initial conditions, and then this other category. And as you can see in the 5.3.1 release of ISAM, this other category was erroneously large. And now in our new release, you can immediately see that this has been made better, and then sense that you will still predict the same bulk concentration, but all of the other contributions were showing more reasonable values to them, and this other essentially went away almost to zero. Now we can look at more. We can march down further and into the further months and see if this kind of holds up, and it does. You see if there's any error grows, and it doesn't. And in fact, all these contributions do look reasonable. Just look at the middle, for example, column. You can see the biogenic contributions in January are typically low unless you get kind of closer to the equator. And then they grow as the northern hemisphere warms up for the summer. And then they kind of peak out in July and later. So that's a reasonable and expected behavior that we want to see. And at the same time, this ALEC category keeps holding out to be kind of low. Again, what we want to see. Now we can look at other things. We can look at regional contributions, because some users, that's what they want to do. Is look at, for example, contributions. Regions like China and India, and all those things look reasonable. In fact, all of them have high contributions. Okay, I'm breaking up again. I'm gonna wait till I get the go ahead. I really apologize for this, but you gotta use the computer they give you at work, not the computer you want at work. So anyways, what I was trying to show you with this slide is that the regional contributions from ISAM are also very much reasonable. Now, depending on how thin you want to slice your bologna, you can do that very thin. And so here is kind of the full extent of all the different things we tracked. It's not really important what all the different sources are, but you can see that there are a lot of them, and the method was robust in tracking all of them. And that's the point of this slide. Now, you might want to see more evidence that, in fact, the contributions aren't reasonable, instead of just kind of eyeballing it. So for this case, I'm going to show you some results from the benchmark case. Now, every CMAC release from the last, I don't know how many, has included some benchmark data, and where we run the model here in-house and then provide the outputs and the inputs to the user communities that then go on, and the users are themselves able to recreate and check against the benchmark data we provided. Since we started releasing things like CMAC ISAM and CMAC DDM, we've also provided a benchmark input and output for those models. So in this release, again, we're providing CMAC ISAM output, and this is for the simulation that I have outlined here. We're providing to the users this CMAC ISAM control file, and here you can see that it's tracking two kind of tag classes. One is sulfate and all the species associated with that, and one is ozone and all the VOCs and NOx species associated with that. And we're tracking four sources. One is the EGU sources from the state of Georgia. One is the fires from the state of Georgia. Then we have also tracking the point source EGUs from North Carolina, and also fires from North Carolina. So everything I'm going to show you here is provided to the users. And in fact, you can go home right now, or you're probably home anyways because it's all remote. You can plot this up and check the same thing I'm showing you and do your own analysis and verify what I'm showing you. So for this case, I'm going to show you the outputs, and also I'm going to show you some quick brute force simulations using this data, because this is a benchmark case. The point is it runs really quickly, so we can do lots of different tests for it. And I will show you some of those tests right now. So first, if you just plot up the outputs of the ISAM concentrations that we give you with this release, and for example, extract them for a grid cell where Chapel Hill, North Carolina is located, this is what you would get. So you would see, this is kind of blocked from my screen, but let me see if I can, you can see that it's tracking all the sources, like I said. And at the beginning of the simulation, you see that this red stuff is the initial conditions that are high at the beginning and that kind of dissipate. And then the blue color is the boundary conditions. Am I back online or am I dead again?
No, we can hear you.
Okay, because it said Zoom is not responding. Okay, it was just kidding. All right, this is awesome. I apologize again. But anyways, the point is that we see the signal from most of these sources, except for something like Georgia fires, which never show up in Chapel Hill, North Carolina, rightfully so. There was a fire event in the southern part of the southern Georgia, southern part of the state, later in the simulation, but it never blows it all the way to this region. The other thing to note here is this black solid line on top is not the sum of the tags. This is an independent variable of the ozone bulk concentrations. And you could see it always lines up perfectly. And that's what we want. We want mass closure between the tags and the bulk concentrations. And we do have that here. All right, so here is some brute force comparison. First, I'm going to show you a few hours from each tag. First, on the left side, we have the brute force from the EGUs in North Carolina, and I just picked a few hours. You can go home and look at all of them if you want. And then on the right side, we have ISAM from the same tag. And you can see ISAM might be a little bit more hot, but it reasonably does match the brute force simulations. And if any of you kind of deeply understand how the brute force method works, you might realize that you don't necessarily want to match it exactly right, but you want to see that the signal and the magnitude of, or the direction and the magnitude of the signal is reasonably correct. And it is in this case. So we can march forward in time to look at some of the other hours, and they get the same story where we are getting the signals in the places where we should be getting it. And then here's another hour at the end of the simulation. Again, the same thing. ISAM ozone may be a little bit higher predicted than the brute force does, but it shows up in the right places. Now looking at sulfate, particulate accumulation mode sulfate from the fires in Georgia. Like I said, there was a substantial fire in the southern part of the state at the end of the simulation, and we are capturing that exactly right, in the right place at the right time. And then as it goes in this fire burned for about 2 days at the end. And as it keeps going, this plume is advected up the coast to South Carolina, and we're capturing that behavior as well. And then finally, here the scale is lower by half. The fire is dying down, and the signal is very local, and then a little bit off over the ocean. I did this kind of a similar thing where I try to calculate the sensitivity or the brute force sensitivity from the boundary conditions of SO2 from both ISAM and the brute force. And again, ISAM is showing higher predictions, but the signal is in the right places. Here's the second hour. Interesting thing to note here, where we might diverge from the brute force in the sense that when you do a difference between two different CMAX simulations, some of those output values, concentrations, and depositions could be negative for various reasons. Obviously, ISAM is not designed to predict those negative values, so we're not showing here. So all these purple things on the left plot are actually values below 0 that ISAM by design is not capturing. And then we can move forward in time on that, and it looks pretty much similar. Now, as I mentioned at the very beginning, one of the main complaints people had with the kind of 5.3 release of the model or earlier was that it was kind of slow. So here, I told you that we've improved the computational efficiency of CMAC ISAM. So here I have a chart that I plotted up, a violin chart of how long it took to run each day of this 14-day simulation on our computer. And so in the red lower left part of the plot is the base CMAC without ISAM. And if for those 14 days, it took about 7 minutes on 32 nodes to run that CMAC per day. Now, if we run the benchmark user case, which has 7 tags as specified, the 4 specified tag, but also boundaries, initials, and other, that takes about 16 minutes. And then I tried a couple of other ones. I did an 11 tag simulation, which took 20 minutes. And then I did a 20 tag simulation, which took 33 minutes on average. And then, you know, the extent of this violin shows the distribution between the different days. Now, still, it does take time to run this thing. So here I kind of provided a couple of tips for you to make this go faster. There's 2 really. One is limit the number of tags. I think some people, when they get a tool like this, the first thing they want to do is track everything everywhere, and that kind of quickly snowballs into a situation where you might not even be humanly possible. It might not be humanly possible for you to analyze and look with your eyes at every kind of output that you're generating and swamping your computer disks with. So really think ahead of what it is you want to see with this and how you might want to set up your simulation to better reflect the goals of your applications. The other big tip that we've noticed very recently is that this, in fact, is very much limited by the I/O part of the model, where writing out the data to the disk does take substantial amount of time. So if you don't need to look at the upper layers of your simulations, then don't write them out, and it will go a lot faster. So when I did this simulation here, I only wrote out layer 1, and that's why it took such a small amount of time. All right, so just to summarize, we've released CMAC ISAM 5.3.2, and I believe that while not exactly perfect or done by any means in terms of improving it further, it is better than the previous release, and I would encourage everyone to use this version over the previous ones, because we no longer erroneously attribute the mass into this other category. And then we, in fact, produce spatial and temporal distributions of the tags that very reasonably match what you would expect from them. Now, as I mentioned earlier, CMAC ISAM or any source apportionment model in general really does benefit from many applications at different scales and different time periods, different domains, and other different things you might want to throw at it. And it's impossible for us as a development group here to essentially try everything that you might want to do. So we would welcome feedback from the community on who's trying to use this model, or any suggestions or complaints, and we will monitor the CMAC forum for those. And as I said, we will continue to evaluate this method and continue to improve it and see what else we can do. So I think that's it. Again, I apologize for the technical issues, but if you have questions, please submit them to the forum here or to me directly. Thank you.
Great. Thank you so much, Sergey. We have time for some questions. I would encourage you to submit them through the question and answer tab, which should show up towards the bottom of the screen. We have a couple of questions coming in. I'll just give it another minute. So, Sergey, let me try and read out these questions for you.
Okay.
So the first question is, if you write to memory at the end of the hour, instead of writing to disk each time, you would increase the performance a great deal. This is from George Delich, I'm assuming.
Yeah, that makes sense. But what I'm trying to say is that you might not want to write it anywhere, but it's the actual output creation step that we don't need that for the next hour. It's not the restart file that I'm talking about. This is just the hourly outputs of depositions and concentrations that I'm saying that you can avoid writing out if you don't want to look at them.
Okay. Question from Dan Cohan. How does ISAM decide whether to apportion ozone to NOx or VOCs?
It doesn't really. it doesn't care. So the previous version of ISAM cared about this chemical regime, which is maybe what you're alluding to, Dan, in that if it was a VOC regime, then the ozone produced during that grid cell in that time was kind of VOC ozone, or if it was NOx regime, and then it was NOx produced ozone. In this case, it's purely essentially statistical or fractional, where it goes equation or it goes reaction by reaction. And for every reaction, whatever the reactant that participated in that reaction fractionally, it gets the attribution to that reactant source. So we don't really look at regimes anymore.
Okay. Another question is, have you thought about comparing results of ISAM with those from OSAT and PSAT from the CAMX model?
Yes, absolutely. And that's in fact what we're doing right now. The difficulty there, as you might realize, is just getting consistent input, excuse me, consistent model inputs for both CAMX and CMAC. And so it sounds like a simple thing, but in fact more difficult than it really needs to be. But we have obtained an episode where we do feel like our inputs are consistent, and we are running that comparison right now. I don't have any
Okay.
preliminary results to share.
All right. When you say match expectations, have you done any independent evaluation of ISAM source apportionment output with PMF or CMB or other ambient or source-based source apportionment methods? Is doing such comparisons feasible?
I'm sorry, I cut out. It's not because I want to avoid that question. It's because I didn't hear the question. Could you repeat it, please?
Yeah, I'll repeat it. So the question relates to, I guess, a statement you made on matching expectations. So the question is really asking of any independent evaluations that may have been conducted in uh, comparing ISAM output with other methods such as PMF or CMB that use ambient data, uh, or and it's also asking is doing such a comparison even feasible?
It is difficult because essentially, if you just look at collecting kind of observational data, you can't really collect observational tag data. But we have done studies in the past, not with this version, but with versions of ISAM. And I think I have a paper out where I looked at comparison with with PMF, I think it was, or one of those kind of observational based source apportionment models, where we could look at tracer species. In that paper, I looked at levoglucosin as a tracer for biomass burning type situations. So it is possible to do things like that. It is very difficult, and you need to have an exactly correct and well described situation and episode to look at. As far as comparing to other tagging techniques and models, we are doing comparisons with things like DDM, with things like the adjoint and other kind of CMAC model world results.
Okay. The next question, Sergey, is asking whether you've thought about addressing the negative apportionment issue, uh, for example, the NOx disbenefit to ozone.
No, essentially, source apportionment, the way that we design it, doesn't really care about those disbenefits. And what the regulatory applications for it really are is you have bulk ozone at specific time and specific location, and then the regulatory application wants to know where to attribute that positive amount of ozone. Now, there are of course situations where those titration situations or titration impacts are substantial and important, and other tools exist to quantify those, such as DDM and adjuvant. So if that is your application and that is what you want to see as outputs, I would direct you to using different tools. And in fact, the IRR analysis will also give you the destruction Oh, no,
Okay, so a question related to that is, um, if you can provide an estimate of the computing time for DDM versus ISAM.
if I can provide it, yeah, I think
Well,
I
I guess
provided it.
so. Lucas Henneman is asking if there's a relative estimate of what it takes to do a DDM calculation versus ISAM for, I assume, a similar
Oh,
problem.
I see. No, we don't have those. I don't have a time comparisons for DDM versus ICM. And you know, it's going to vary based on your system, based on your environment, your different compilers you've selected, and what your application is. So it's there's not really a magical, you know, if you run CMAC ISAM, it's going to take you X, and then if you run DDM, it's going to be Y. So I can't really give you those quantities.
Okay, we have a few more questions that are coming in. So the next question, Sergey, relates to the implementation, and the question is if the gas phase mechanism or the aerosol treatments are modified uh, in CMAC, do we need to make changes to ISAM, or does it automatically work with the updated mechanism and aerosol treatments?
Right. So that's kind of the beauty of finally embedding this thing inside a CMAC and releasing it with the CMAC model, is that there's less maintenance upkeep type situations like that. And in fact, as I mentioned earlier, this should work for every chemical mechanism released with CMAC. Now, I didn't try them all. I'll be honest, but the way that we designed it, it should be compatible with those. So, and whenever those mechanisms are changed, those changes should be propagated. Now, it really depends on what changes you're talking about. So if we're just talking about changing some reaction rates or adding a couple of new reactions or having kind of minor changes to chemistry or any kind of physical process in the model, those should translate fairly well to the model. But if you're talking about big structural changes or big changes to the methodologies, then it would probably behoove you to make sure that those changes are correctly propagated to the tagging the routines as well.
Okay. The next question, I'm not sure if I understand it completely, but I'll read it out, and maybe the person who's posing the question might be able to clarify a little more. So the question is, can ISAM provide information on whether PM nitrate came from SOx or NOx?
It can if you are a little bit clever with it. As I said, we are attributing to emission streams. So it's not gonna tell you what species in that stream uh, contributed to the production that you see in the output, but you can be a little bit tricky and take your emission streams and split them by SOx and NOx and have different streams where you have a stream that's only SOx and a stream that's only NOx. And then you track those, and then that will give you the attribution to just those species.
Okay. We have still many questions coming in, so I'll ask you, maybe we can go through another two of these, and then perhaps in the interest of time, we should move to John, and then come back to additional questions after that talk. So let's just do two more questions. I think it's great that there's so much interest in what you presented, Sergey. So the next question is, for the initial conditions to update tag concentrations in CMAC 532, how is the value of loss fraction, which is 14 in the code, determined? Do you know what?
Yeah, that's a good question. And if Bill Hutzel is on this, he'll give you more information on that. If not, I know there's a forum post asking this question. I don't know, I don't remember why 14 was the number, but that's what it is. And I will try to get myself over there to answer it, and or better yet, I will get Bill Hutzel to answer that question. Check the forum.
Okay. Um, can ISAM be applied for operational air quality forecasting to obtain forecast of source apportionment in real time?
Yeah, I don't see why not. If you're running CMAC forecast using 5.3.2 CMAC, and I honestly don't know what kind of changes you're making to the model to enable that forecast mode. But if that's what you're doing, if you're using 5.3.2, then yes, it will give you output for apportionment as well.
Right. So I reckon as long as you have the computational resources to run it, you should be able to do it. Okay. Last question. Can you provide some information on ISAM rural versus urban areas? I'm not.
I'm sorry, could you repeat that? I got cut out again.
Can you provide some information on ISAM rural versus urban areas?
I can't, but you can if you apply it to your application.
Okay. We may be able to come back to more questions after John's talk. So thank you very much, Sergey, for a very good talk and for answering so many questions. Okay.
Yeah, I'm not.
Were you saying something, Sergey?
I'm trying to get out of this now. If somebody can kick me out, that might be better. I might have to just shut down my computer and rejoin because I cannot get out.
Okay, I think John has been able to share his screen. So John, we can see your slides whenever you're ready. So just a quick introduction. John Pleim works with the Office of Research and Development and at EPA. And he has been leading a project investigating the development of the advanced air quality modeling system, sort of looking at how the science in our atmospheric model should evolve, and looking at methods to address that. So over to you, John.
Okay, thanks, Rohit. So can you all hear me okay? Rohit, can you?
Yes.
Yeah, okay.
Yeah.
All right. Hopefully my system won't flake out. It did. I lost Zoom entirely a little bit during Sergey's talk, so hopefully it'll hang together. Anyway, so as Rohit said, I'm going to talk about the advanced air quality modeling system, and this is mainly focusing on our global MPAS CMAC model. And I'd like to acknowledge all my co-authors. This is quite a large team effort. And let me move into it. If I can move these slides forward. They're not. Oh, there we go. Okay. So the EPA has embarked on the Advanced Air Quality Modeling System project to develop the next generation air quality system. And we wanted to include these attributes: integrated meteorology and air quality, global and regional coverage, seamless mesh refinement for global to local scales, state of the science meteorology and air quality modeling with continuing development and community involvement. So to do that, we're developing the coupled MPAS CMAC system. And the global MPAS CMAC system complements the continued development of our regional WRF CMAC system, which operates either online or offline or in a coupled mode. We're also working on a regional MPAS CMAC capability that will use meshes that exactly fit into a global mesh And so it won't need any interpolation. MPAS is the model for prediction across scales. This is a model that's developed at NCAR by the same group that developed WRF and still supports WRF. And like WRF, it's a fully compressible, non-hydrostatic model. Unlike WRF, it uses finite volume discretization, and the grid cells are no longer rectangular, but they're actually mostly hexagons. And although there are a few pentagons here and there. And it can be run either as a uniform coarse mesh, like you see in the example on the left. And that's a very coarse mesh at about 250 kilometers. And you can see it's a bunch of little hexagons like a beehive. And then it also can be run, and this is very attractive for air quality, as a non-uniform mesh with refinement. And so this example has 92 kilometer resolution with 25 refining down to 25 kilometers over North America. You can't really see the little cells because they're too small. Anyway, this is the mesh that we're using to test the WRF CMAC configuration. So, I mean, not WRF CMAC, I'm sorry, MPAS CMAC. So MPAS CMAC is a coupling of MPAS version 7.0 and the CMAC 5.3.2. And so these are the latest versions, and we will keep these up to date as time goes on. CMAC is actually called as a module within MPAS with a two-way data transfer using a coupler that's very similar to the way MPAS couples to physics modules within the MPAS system. MPAS has been revised. We revised it with our own physics and in our four-dimensional data simulation to make it more suitable for air quality. So these are basically the same things we've been using for years in WRF to drive CMAC. Unlike our current system, the advection of the chemical species is now done in the meteorology model in MPAS. And so the chemical species are treated just like meteorological scalars. And so the advection of CMAC is turned off when coupled to MPAS. Also, there's no need for any mass adjustment for continuity in CMAC like we've had to do when we're coupled to WRF. The latest version of Megan 3.1 is inline in the system, and this produces the global biogenic VOCs as well as the soil NOx. The CMAC includes detailed treatment of halogen chemistry as well, and it also uses the CAMS reanalysis, which is a system from ECMWF in Europe to provide ozone from the stratosphere. Being a global model, there's no lateral boundaries, so what's in the model stays in the model. It just circulates around the world. So it's very important to specify the ozone in the stratosphere accurately, because this will be a source of ozone as time goes on throughout the whole model. The halogen chemistry is basically bromine and iodine, and this chemistry is quite detailed. It's using gas phase, heterogeneous phase, and aqueous phase reactions. The halogen chemistry reduces ozone over the oceans. And we found when we run the hemispheric WRF CMAC, it reduces ozone by about 21% over the oceans in the northern hemisphere. And very similar, when we run MPAS CMAC, it reduces ozone by about 22% over the oceans. And this agrees very well with other work. And in Geochem, they had similar halogen mechanisms, and they reported losses of about 19%. And we're also working to further revise the halogen chemistry and continue to advance it in CMAC. On the bottom, you can see where the depletion is. Vertically, it's mostly near the ground in the bottom kilometer or so. And then spatially, it's over the oceans, although that will affect some of the coastal areas. So first, I'd like to talk about the changes we made to MPAS for its meteorology. And like I said before, we want to make the model more suitable for air quality. So we're basically bringing in the physics and the data simulation that we've used for many years in WRF. And so these are systems that, or models that we've developed here in APA, ACM2 boundary layer model, the PX land surface model, a revised version of the Kane-Fritsch convective cloud scheme that includes radiator feedback and dynamic lifetime. So all these we added to the MPAS model, and this is all published or is about to be published in a paper by Rob Gillum, and I'll show that later. All the modified physics is the same in the latest version of WRF and MPAS. And we've also added data simulation. This is work of Russ Bullock. He's implemented the four-dimensional data simulation, very similar to what's in WRF. This is important because we typically run long periods of time, like a year or more, without any restarts, because we don't want any discontinuities in the meteorological fields. So to do that, we found that simple FDDA or four-dimensional data simulation works very well. The other thing we've added is the indirect soil moisture data simulation in the PX land surface model. And this is the same as we've been doing for many years in WRF. The land use is a blending of the NLCD, which is very highly resolved and highly accurate, but it's only available for the US, with the global data set from MODIS. And so the land use it includes subgrid fractional coverage, meaning that every grid cell has the fractional amount of every land use type. And this is important for calculating the surface fluxes, both meteorologically and chemically. Model evaluation, we mostly use the AMET tool, the latest version. So, and here's the reference for Rob. So what Rob did, he ran the model with two mesh configurations, a coarse mesh, 92 kilometers, we're finding down to 25 over North America. And then a finer mesh, 46 kilometers, we're finding down to 12 kilometers over North America. And these we ran for the full year of 2016. And for comparison, he compares it to the 12-kilometer continental US WRF simulation for the same period using most of the same physics. These are continuous simulations using FDDA, 10-day spin up mainly for the soil moisture. And so that's just at the very beginning, back in December of 2015. And after that, there's no reinitialization. The physics is, as I've already mentioned, the EPA modifications, and all the other physics is the same between the MPAS and the WRF, with the exception of the microphysics. In WRF, we use Morrison. We found that to work very well over many years. But in MPAS, Morrison is not available as of yet. So we're using the WSM6. FDDA is applied the same way, nudging of temperature, humidity, and winds only above the boundary layer. And this is analysis nudging. So we're using, for MPAS, we're using the quarter-degree GFS analysis, which is a global analysis from NOAA-NCEP. And then for WRF, we're using the NAM12, which is the North American Mesoscale Model Analysis, also from NOAA-NCEP. The indirect soil moisture and temperature nudging in the PX LSM uses surface analyses that are based on the NAM12 blended with the global GFS quarter degree for the MPAS. And then for WRF, it just uses the NAM12. Rob did an evaluation looking at 5 different runs, 4 different MPAS runs, and then the WRF 12 as kind of the benchmark and really kind of the target to get to look at the errors and the bias in the system. There's MPAS was run with 2 resolutions, as I've already mentioned. So we're calling that MPAS 12, MPAS 25. And then the third one here is MPAS OG, which means OBSGrid. So what Rob did is he reanalyzed the NAM12 for the North American part using the OBSGrid routine, which basically reanalyzes using all the observation data, all the surface observation data that's available. The surface meteorological network is quite dense, so this really makes a pretty large improvement in the surface analyses. And then for comparison, we also included this MPAS NOAA, which has a lot of the same physics, except for boundary layer, it uses YSU, and for land surface, it uses NOAA, the mosaic option of that. And this we obtained from Patrick Campbell, who's now at NOAA. The only other difference is, well, there's two other differences. One, I mentioned the soil assimilation in the PX. That's not available in NOAA, so it doesn't have that. The land use data for the MODIS NOAA run just used the MODIS for the whole globe. So it didn't include the NLCD part. So here's some of the statistics. This is 2 meter temperature, root mean squared error. These are daily averages for the entire year, broken up by quarters. Winter in the upper left, and then going to the right, spring, and then lower left, summer, lower right is winter. And you see all five models represented in these different colors. And almost always the WRF 12 is the lowest error. That's our target. And we're getting close to that. And you see that the MPAS OG is generally the best MPAS option, MPAS configuration. And in fact, in the summer months in the lower left, the MPAS OG, which is this orange line, is just as good as the WRF 12, really pretty much the same error. So we've really achieved a goal of matching the benchmark of the WRF 12 there. But you also see that the OG or the OBS grid did add did reduce some error, because you compare it to the blue line, which is the same model without the OBS grid, and that's a little bit worse. And then the red line is actually a little worse than that, showing that resolution also matters. The green line, the NOAA model is much higher error, and that's likely primarily due to the lack of this soil moisture nudging using the surface analyses. Going on to water vapor mixing ratio, the winter, the errors are pretty low because the water vapor mixing ratio is rather low. But again, the most interesting one is the summer in the lower left. And you see a little bit more separation among these model runs. And in this case, the MPAS, even with the OBS grid, didn't get quite as low as the WRF run. And we think this may have something to do with the microphysics, and we're working on testing that. Spatially, this is 2 meter temperature for winter in the left column and summer in the right column. The top row is the MPAS OG, which is our best results from MPAS. And you can see that the dots are blue and even shading into dark blue in some of the areas in the east, particularly in the summer. The dark blue is getting down to like 1 degree error. And so that's quite good. If you look in the middle row, this is the comparison or the difference between the root mean squared error for the MPAS OG minus the error for the WRF 12. So wherever it's red, it's saying that the MPAS run was a little bit worse, and wherever it's green or blue, it's better. And all the other stuff is pretty much the same. And so what you see in here is that in the winter, there's this big red blob in the north central part of the US and going into Canada. This is showing that the MPAS run was worse, and it actually is, well, I won't say it's too much worse, but about 1/2 degree worse, which is significant. And so this makes it, this really is concerning. In the summer, you don't see that. And in fact, in the summer, 65% of the sites show lower error for the MPAS OG compared to the WRF 12. The bottom row is showing the difference in error between the MPAS OG and the MPAS 12. So this is showing that, again, the effect of using the OBS grid for reanalyzing the surface data, it does help. And in the winter, it improved the error in 71% of the sites and 64% in the summer. So one thing we wanted to look at was the effect of the microphysics. So we wanted to compare what happens when you run with Morrison microphysics versus WSM microphysics. Since Morrison is not available in MPAS yet, Rob made these comparisons in WRF. And so he did one run with Morrison and one run with WSM. And this is a comparison or the difference in the root mean squared error in January. And you see at most of the sites, there's not a lot of difference, but in that same area in the north central part, you see quite a large difference. In fact, it's showing that when you run with the Morrison microphysics, you decrease the error substantially, 0.5 degree and occasionally up to almost 2 degrees in some of these areas. And if you remember the previous slide, in fact, you don't have to remember, I'll just go back. It's the same area. It's almost exactly the same area. This red blob here corresponds with this blue blob very well. So what that tells us is that the reason that the MPAS is not doing as well as the WRF run is likely due to the fact that it's using WSM6 microphysics rather than Morrison. We are adding Morrison to MPAS. If someone else doesn't do it before we do, we will do it. And then we expect to see those errors diminish or disappear, really. Precipitation broken up by quarter of the year. The left column is PRISM. Those are the observations. And then we have comparisons with MPAS 12 in the middle and WRF 12 on the right. And you see both models are doing quite well in reproducing the patterns in each season. There are some differences. There's a general underprediction most of the time, particularly in the summer. And you can see in this July through September period, there was a lot of precipitation in the middle part of the country that MPAS and WRF underpredict. WRF underpredicts it actually a little bit worse. So MPAS is doing at least as good, in fact, a little bit better than WRF, particularly in the spring and the summer. We looked at solar radiation reaching the ground, and there's a global network of the baseline solar radiation network of all these sites across the world. And so we did some analysis just in the US. So this is the SURFRAD sites in the US, and compared MPAS to WRF. On the top is the mean absolute error. And so you see that the MPAS is a little bit worse. The MPAS 12 is actually a little bit worse than the 25 in this case. In the lower one, you see the bias. And so what this is telling us is that there's too much solar radiation in all of these models, and that the MPAS is worse than the WRF. So this suggests that the cloud cover is not enough. Again, this may be due to the microphysics, so we will revisit this when we are able to use Morrison microphysics in MPAS as well. So finally, I'm getting to the air quality part where we coupled MPAS to CMAC, and here we just used the coarser mesh configuration, 92 refining over down to 25. We used all the same physics and assimilation that I just described. For emissions, we're using the beta version of the NEI 2016 NEI, much like we do with WRF CMAC. And then, but for the rest of the world, we're using anthropogenic emissions from HTAP. We had to grow this to 2016 with scaling factors. And we've also supplemented that for a special emission database for China that was provided by Tsinghua University. The biogenics are from Megan, and the lightning emissions are climatological from Gaia. And this picture is just showing an example of the NOx emissions on a particular day across the world. The Megan produces biogenic VOCs, and this is a big improvement, adding the Megan version 3.1 inline into the MPAS system. So it's computed on the same resolution using the same meteorology as the MPAS run. Previously, we had an offline data set of Megan 2.0, and you see it was much coarser mesh, and actually the magnitudes are also a little bit different. So this does have a significant impact. We're using Megan rather than BICE because BICE is not set up to go global. And also Megan is a state of the science model that's continually being developed. Megan also produces soil NOx emissions. And in fact, it has two models for that. The older model, YL95, is the same as that we've been using in BICE and in the WRF CMAC for quite a few years. So this is what we're using in these tests right now. But there's also a new one, the Berkeley-Dalhousie model, just published a few years ago. And when we test that in terms of emissions, you can see that it produces a lot more NOx. So we're very interested to see what this does to our MPAS CMAC air quality simulation. So we'll definitely test that. So our testing right now and evaluation is for July 2016. We set up the initial conditions. It's basically a hot start for ozone. So we've prescribed the ozone in the full three-dimensional mesh on June 21st. So we got 10-day spin up before July from the CAMS reanalysis. As I mentioned, CAMS is a product of the ECMWF. It's using a lot of satellite data for ozone. So it's really about the best you can do for defining the stratospheric ozone. So I kind of get ahead of myself. So the stratospheric ozone is continually assimilated from the CAMS reanalysis every 6 hours, but it's continuous. And wherever, only in the stratosphere, so wherever the model is above, the model concentrations of ozone are above 500 ppb, and wherever, forever all the layers above 300 millibars or hectopascals. So we ran it with a 10-day spin up for all of July, and we evaluate only for July. Here's a really cool little animation that Jeff Willison made. And you see, this is ozone at the surface, and over the US, there's a lot of detail. So this is a very high resolution part. You can also notice that there's ozone being transported around the globe, particularly here from North America, all the way across the Atlantic Ocean and running into Western Europe. At the beginning, you probably missed it, but you could also see ozone coming from Asia into the west coast of North America. In the other parts of the world, you can see that the grid cells are much bigger. Some of the other features, very high ozone in Eastern China, but also in places like Tibet because of the high altitude. The ozone in the oceans is pretty low, particularly in the tropics. That's largely due to the halogen chemistry. And so what we've done, let's see if I can move on. Yeah, here we are. So we started evaluating this by doing what we usually do and compare to the AQS and the NAPS network in Canada. This is for average hourly ozone for the whole month of July. And in the upper left is the observations, and in the middle is the MPAS CMAC results. And you see it's looking very similar in terms of the pattern, but the concentrations are somewhat lower. And on the right, you see the difference. So this is basically the bias. And in the east, there's not much bias. Most of the sites are gray, which means it's within 5 ppb. But there are some that are green and some yellow, which means they're 5 to 10, either plus or minus. But the biggest biases are in the west. All this blue and green is showing under predictions, and particularly the dark blue in the central part of California, the Central Valley. These are down, 15, 20 ppb bias, low bias. So this is quite significant. Why is this? I think, and I'll mention this a few more times, I'm sure, but I think it's mainly because the resolution is only 25 kilometers, which is really not sufficient to resolve the flows that are happening in California, very complex terrain and flows coming in from the ocean and so forth. Generally, we feel like you have to get down to about 4 kilometers or finer to do a decent job doing ozone in California. And if in the lower left, you see the hourly box plot for the nighttime hours, the model is fairly close, but in the daytime hours in the middle here, you can see there's a very distinct low bias. And since this is averaged across all the sites, it is dominated by these low, very low under predictions out west, and particularly in California. So for the max 8-hour average daily ozone, you see similar picture, but actually more low bias, since the low bias was mostly in the daytime. And you see not only the low bias in California, but we're seeing more low bias in the east as well. You compare that to the WRF CMAC. This is 12 kilometers. This is higher resolution. And you see the WRF CMAC also had a low bias in California, but not as bad, because even 12 kilometers is not enough to resolve the flows and the photochemistry in California. PM is looking pretty good. This is the hourly observations averaged over the whole month from AQS and NAPS. And the gray is within 5 micrograms per cubic meter, and admittedly that's a pretty low bar, but most of the sites meet that. There does tend to be a low bias in all these green ones, like 5 to 10 pretty much, and you'll see most of that's down in Texas area and the Gulf Coast region down into Florida. For comparison, the 12-kilometer WRF CMAC is showing very similar pattern of low biases in the same places. Not quite as much, but pretty similar result. The organic carbon from the 12-hour averages of Improve and CSN are shown on the upper right. And here the gray area is plus or minus 1 microgram per cubic meter. And so almost all the sites are within that, which shows quite good agreement with the observations. There is some overprediction in California. In the lower part, you'll see isoprene, just an example, showing that indeed the MPAS using Megan typically does produce more isoprene than the BICE in the WRF CMAC system. And we move on to Europe. Now out here, the mesh is even coarser. It's 92 kilometers. So we're not able to resolve the ozone very well at all. Observations from EMEP are on the left. In the middle is the model results, and in the right is the difference. Pretty high biases in the Alpine region, and as well as in the Mediterranean. 92 kilometers is not going to resolve those features very well, so this is not too surprising. To look what's happening around the rest of the world, one thing we can do, there's other things and we haven't got to them yet, but one thing we can do is look at ozone sondes. This is one of the networks here shown with these red dots. So we can learn several things from ozone sondes. One, we can evaluate the stratospheric ozone assimilation and see how well that works. And you can see on the left plot, this is an example from Pago Pago, I'm not sure how to say, out here in the South Pacific. And you see up in the stratosphere, the model matches the ozone sonde very well, since a lot of this ozone is coming right from that reanalysis that uses a lot of satellite data. So there's a lot of actual observation already baked in here. However, in the tropopause, the model is too low, and this low bias goes all the way down to the ground in this case. Another thing we like to look at is the PBL structure in these remote areas. And you see both the potential temperature and the water vapor mixing ratio. In this case, they're showing that there is a pretty well mixed boundary layer, a shallow one, but it's pretty distinct. And the depth of it matches the ozone sonde quite well, although it's clearly too dry. Another example from another network of ozone sondes, this is SHADOWS that focuses on the southern hemisphere. This is from Reunion Island, which is a little island off the coast of Madagascar. Here you see much the same thing with the ozone. Very good in the stratosphere, low in the troposphere, right down to the ground. For the boundary layer, it's got a well-mixed boundary layer, but it's too shallow. The reason it's too shallow is because the grid cell is very large, 92 kilometers. We're not resolving the island very well. But the island is substantially large, so it does affect the ozone song, which is launched right in the middle of the island. So the ozone song looks more like a land-based boundary layer, and the model looks more like a marine-based boundary layer. Another thing we like to look at is ozone sondes that are on the edge of the western edge of the continental US. So this gives us some idea of the ozone flowing into the country. And this is important because the ozone in the free troposphere, especially the lower free troposphere, is very important for the source of entrainment when the boundary layer grows up into it every day across the whole domain. So if we can get the ozone pretty well in this lower free troposphere region, then it's very good for reproducing ozone across the whole domain, or across the whole country, I should say. And there were a lot of ozone sonde launches at Trinidad Head. There were 6 during this modeling period. There'll be many more when we do the full year. And you see the model's doing quite well, matching the ozone sonde throughout the troposphere and, of course, the stratosphere for many of these days. Although a couple of days, it is distinctly low in this lower stratospheric or tropospheric layers. So in conclusion, we feel the model is ready for full year testing and evaluation. The run we've done so far, the 1 month with the hot start and the 10-day spin up for the soil moisture, is showing that there's generally daytime under predictions of ozone, particularly in the California Central Valley. Ozone is also too low in Europe and tends to be too low at the global remote ozone sondes, although I only just showed you a couple of those. There are quite a few more that we haven't finished looking at yet. Possible reasons: resolution, as I keep mentioning. 25 is too coarse for California. 92 is too coarse for Europe and probably other places around the world. A big one is there's not much spin up. There's really hardly any spin up at all in this particular test. When we do the full year, we're going to start on October 1st of 2015. So that'll have a 3-month spin up before the year even starts. And then by the time we get to the summer of 2016, we'll have at least 9 months. So this ought to have a pretty significant effect on the tropospheric ozone. We'll try switching on the new soil NO emission model, and no doubt that will increase ozone because it increases NO. The PM 2.5 is looking fairly good, especially the organic carbon, and it's doing much better with the new Megan than it had previously. Next steps, we're working on some more developments. Bidirectional flux of ammonia from fertilizer using satellite assimilation. Global lightning assimilation to improve the precipitation from the Kane-Fritsch scheme using worldwide lightning location network. Lightning location network. And the same network, the same global lightning network we'll use for NOx emissions. So this will be an improvement over using climatological lightning NOx. And we're working on regional capability, both to couple a regional WRF CMAC as well as a regional MPAS CMAC. So we're testing the evaluation of driving a regional MPAS CMAC with global MPAS CMAC lateral boundary conditions. We now have the capability to create customized meshes thanks to Russ Bullock. And we've already made a new mesh that we're going to try out, get some higher resolution. And we're developing a method to create the regional mesh with refinement so it can get to very high resolution and it fits exactly within a coarse uniform global mesh. The advantage of this is that you can run a coarse global uniform mesh very quickly. It'll take very little computer time, and we can run it. So we can run it for years and get a really good spin up of the global chemical situation. And then we can use that as boundaries for a regional mesh that fits exactly within the cells that are from global mesh. So there'll be no need for any interpolation, and we can run a much shorter period with a higher resolution that costs a lot more, but we'll have the benefit of the longer spin up. We'll also develop the tools and evaluate driving WRF CMAC with these same global MPAS CMAC simulations. So that's it. There's all the references are here for you to look at later on. Thanks a lot. I'll take any questions if you have any.
Yeah, so please use the question and answer box towards the bottom of the screen. So some questions have already come in, John, and I can read those out for you.
Okay.
So the first question is, I'm wondering if the percentage of canopy and impervious covers is globally available to be able to use the PX LSM option to its full potential. MCAR's WRF only provides that information for the US.
So the impervious and the canopy fraction, was that the question?
Yeah. Is that available globally?
No, that's at least not, we don't have it at this point. That's part of the NLCD data set, which we only have for the US. So no.
So I guess the question is, what are the implications of not having that data set for the PX LSM?
The implications are pretty minimal for the course resolution that we're using outside the US. It really helps mostly in urban areas, and we're not resolving them at that scale. But we do have it over the US, and so we are benefiting from it in the US part.
The next question relates to the chemical mechanism. What was the chemical mechanism used in MPAS CMAC versus the WRF CMAC comparisons?
It's the same. It's the CB6R3. Is that right? Rohit knows this better than I do.
Yeah. So they are the same flavor of the CB6 mechanism.
Yes, and the aerosols are the same as well.
Yeah. So I guess the CMAC configuration in both is exactly the same, whether it's coupled to WRF or to MPAS.
That's right.
So the question is, so is species mass conserved in MPAS CMAC, unlike CMAC 5.3?
The mass is very well conserved. The first thing we did when we got a hold of MPAS is test mass conservation, and I mean it's very, very good at that. And so since we're doing all the transport in MPAS of the chemistry, then the mass is precisely conserved, and we don't have to do any adjustment like we do in the WRF CMAC. The reason we have to do it in WRF CMAC is because CMAC has its own advection scheme, which is not exactly the same as the advection going on in the dynamics going on in WRF. In MPAS, it's all consistent, so there's no need for any of that.
For the offline CMAC, is there an interface available to convert MPAS output to CMAC ready MET input?
No, there's not. And we don't really envision creating such a thing, because to run globally, you really have to use the MPAS mesh, which is this Voronoi hexagonal mesh thing. And the advection on that mesh is quite a bit more complicated than the typical, XY two-dimensional advection. So we don't see the value in trying to reproduce that. And if you just want meteorology to drive a regional version of CMAC, then you're better off just using WRF. That's what it's designed for.
But eventually, we do expect that there will be a regional version of MPAS.
Oh yeah, Oh yeah, there's already a regional version of MPAS. We haven't developed the regional version of MPAS CMAC. That's really just a matter of creating the boundaries and making the chemistry interface with the global system like the meteorology does. So, but that's ongoing development right now.
The next question is asking, was the good comparisons of the vertical profiles with the ozone soundings due to the FTDA scheme for assimilating ozone from the CAMs?
Well, the reason it's so good in the upper layers in the stratosphere part is, yeah, it's definitely from assimilating the CAMS reanalysis, and that's intentional because we know that that's important for, it's an important source for ozone in the troposphere. And I think one reason our troposphere tends to be too low, tropospheric ozone, is that we haven't spun it up enough. We did a hot start and we used the reanalysis for that, but the CAMS reanalysis is probably not all that, is not very good in the troposphere. It's really good in the stratosphere because the satellites are good at detecting stratospheric ozone, but they're not so good in the troposphere where the concentrations are much lower and the signal's already being shielded by the high concentrations in the stratosphere. So the hot start helps a lot, but it's not going to entirely make up for the lack of a spin up. I think if we had a really long spin up, then a lot of that stratospheric ozone will have time to transport down into the troposphere and bring it up to a more realistic level. So that's what we're working on.
Okay, we have several more questions. Before I get to them, just a quick clarification with the organizers. Even though we are past the 2:30 time, I'm assuming it's okay to carry on. Brian or Saurav?
Go ahead, Rohit, but I think we should stop by 2:45 so people take a break before the social at 3.
Okay, all right, we'll try and do that.
Thank you.
So when creating the regional mesh that could fit with the coarse global mesh, are there any restrictions on the resolution of the regional mesh? John?
I don't think so. I think it's a very tricky thing to do this. This is what Russ Bullock is working on. And it's very tricky to create a regional mesh that fits into a global mesh, and when they're constructed a little bit differently, because they really have to match exactly. Russ has had some success, and he thinks he has it. He hasn't done a lot of it yet, but I don't see any reason why you couldn't have, because all the refinement is going to be in the regional part. So I don't think there's any limitation on how much you can refine in the regional part.
Okay, the next question is asking for a clarification on for regional applications with grid resolutions finer than 12 kilometers, is VOR-CMAC still the model to use and essentially use MPAS CMAC for providing the boundary conditions? What is the finest resolution of MPAS CMAC?
We haven't done more than what we've shown. MPAS there have been model runs of MPAS, I know, at 3 kilometers. I'm not sure if others have exercised it any finer than that. I wouldn't be surprised if they had. And there's no technical reason we couldn't run MPAS CMAC at 3 kilometers or whatever MPAS runs at. I don't think there's any real hard, fast, lower limit to it. So as a practical matter right now, I mean, when we have a project to run, say 1 kilometer or so, we're still using WRF CMAC. And I don't see that changing anytime soon. Because generally when you're doing that kind of resolution, it's a very small area. And so having the whole thing run globally is really not very important. But I do envision in the longer run, when we do have this system further developed, that you can run a regional domain with very high resolution on the order of 1 kilometer or so, that does get its boundary conditions from the global MPAS CMAC. Either running a WRF CMAC at high resolution, interpolating from the MPAS CMAC that ran globally for long periods of time, or doing what I just talked about, having an MPAS CMAC regional model that meshes precisely into the global one, but refines down to those levels. So that's certainly feasible, and we want to have that capability, but we don't have that yet.
Okay. Can MPAS CMAC be coupled with MPAS Ocean to explicitly simulate SST and dynamically represent air-sea interactions?
You're saying to interface with the ocean?
With the ocean model in MPAS.
I would think it could be. We haven't tried that, but that's an interesting question, and we've thought of that, but we haven't pursued it. But theoretically, certainly could.
The next question is asking whether there are ways to improve ozone simulations in the South Coast, California.
Higher resolution, I think. Beyond that, I that's not really the subject of this work. I think others could address that better than I could.
Okay. Okay, so the next question relates to CAMS reanalysis, and it's asking whether one really needs to run the CAMS model, or can those fields be obtained? What's the approach to bring in the CAMS data into the MPAS CMAC? How does one go about that?
And we don't run it, that's for sure. It's already produced. It's a product from ECMWF. I didn't do the acquiring of that. That was Jeff Willison. He could probably answer that a lot better, but I think it's pretty freely available. It can be downloaded and used.
And it is day specific, right?
Excuse me?
It is day specific data.
Oh yeah, yeah. We're using every 6 hours, day specific, yes.
Okay. Talat is asking, can you provide an indication of computational resources needed to run MPAS CMAC?
I could give you very rough numbers just from our recent experience. One issue is the halogen chemistry currently is slowing things down, maybe 20%. We'd like to improve that, and we will work to improve that. I don't know if we'll be successful or not, but right now with the run with the full detailed halogen chemistry, I think it was taking 4 hours, 20 minutes or so, roughly, on 256 processors per day. So that's pretty extensive. I'm hoping, I mean, if without the complicated, or I should say the detailed halogen chemistry, it's more like 3.5 hours per day. on 256. And if I got those numbers wrong and someone's, particularly David Wong, is there to correct me, maybe he could do that. But that's what I remember.
Okay, very good. I think this is the last question, and it came in the chat box. How are the global biomass burning emissions handled in MPAS CMAC? And what are the implications for the PM 2.5 evaluations you showed?
Yeah, that's a good question. The wildfires are brought in. This is not my area of expertise. George Pulio could answer this much better, but in the U.S. part, it's through the NEI, and however it's done in the NEI, and that it does use. I know it does use real wildfire information to do that. It's not, climatological or whatever. In the rest of the world, it's the FIN system, I believe, FINN.
Yeah, that's correct.
Yeah, Rohit knows this better than I.
Yeah, and George just confirmed that in the chat box too.
Okay, good.
So FIN is used globally, and then SmartFire for the US.
There you go.
Okay, I believe that was all the questions that we had for John. And so we are approaching Saurav's deadline of 2:45. And I would like to thank both our speakers for very informative talks, and for everybody who dialed in for active participation, and the great questions. So with that, thank you very much for joining us. I will hand it back to Saurav in case there are any announcements that he needs to make for the social hour.
No, we are good. Thank you, Rohit, and thank you to the panelists, John and Sergey again. I think we are good, and we will reconvene at 3 for the social. BH walked through the instructions early in the day. So we'll see you all at 3 o'clock. Thank you again.
Great. Thank you very much.